Alright, here we are again, Chapter 8, about the atomic structure. So let's get into the last part of this course, and some cool stuff to look at. Let's get into it. The general picture here, process, I guess, we're going to be applying Schrodinger's equation to the hydrogen atom, proton and electron, and see what the results are, and then kind of take that picture and what we get from it and extend it to other elements, so more and more protons and then more and more electrons, and you start to see kind of where some of the fundamental structure of the periodic table comes from and some properties of the different elements and why they line up in a certain way. Here we just have a picture of the emission from some nebula. So it's colorized, where you're seeing the different colors are based on the emission lines. That process of looking at the emission spectrum of elements like hydrogen, helium, so forth, that is still centrally important in what we're going to do, and understanding that emission allows us to analyze stuff that's very far away just by seeing what lines, emission lines, that we see when we look out at this distant stuff. So like I said, we're going to look at the hydrogen atom, which is just a proton, has a positive charge, plus E, and one electron, negative charge, minus E. So even though we have this new idea of quantum objects like electrons, protons, photons, that they act as waves and as particles, and we describe them with wave functions, which are related to probabilities. To get going and understand the atomic structure, we still are going to kind of rely on Bohr's idea and think about a hydrogen atom as this sort of planetary setup, where you have this center that's basically stationary, the proton, and the electron is whizzing around that. And in that case, the potential in this situation is the Coulomb potential. There's technically a gravitational potential, but it's incredibly tiny relative to the strength of this Coulomb potential. So we can ignore gravitational potential here and just think about the Coulomb potential. Remember, it's related to the electric force, Coulomb force. And it looks like this, right? It's negative. It goes as 1 over r, the inverse of the distance between the proton and the electron. It involves the charge of each of them, so you get 2 factors of E, one for the proton, 1 for the electron. And it also has, just write it as K here, but that's that 1 over 4 pi epsilon naught. So if this is the potential that we're talking about, think back to Schrodinger's equation, right? You have like the piece that's kind of has to do with kinetic energy almost, and on the other side you have the total energy, and then the only other thing that changes there is that potential, U. So we're still only dealing with the time-independent Schrodinger equation here, and yeah, the time evolution part is not that complicated in this situation, but it's just more than we need. We don't really need to worry about that. What we do have, though, is now three-dimensional equation, where we have x, y, and z, not just x anymore, because r is a radial measurement, and so it's a three-dimensional measurement. And yeah, we just need to take into account that this is a three-dimensional setup now. So instead of just a d by dx squared of psi, you have that d by dx squared, d by dy squared, and d by dz squared. Don't worry too much about this. It's quite complicated, and we're not going to worry about actually understanding the process of getting to the solutions. It's going to kind of tell you a bit about the process, and then we're going to look at the results, and we're going to see the implications of those results. So just a little bit about the process that you have to go through in order to get to these solutions. For one, it makes a lot of sense to transform from rectangular coordinates, x, y, and z, to spherical coordinates, because the potential is spherically symmetric. It only depends on the radius. Hopefully you're fairly familiar with spherical coordinates. You are defining a point in space not by its x, y, and z coordinates, but by its distance to the origin, r, and the angle it makes from the z-axis, we're calling that theta here, and then the angle that that point makes if you project it down onto the xy plane, the angle that it makes from the x-axis. It's phi here. And so these are very well-defined things. You can see how they're related to x, y, and z, and basically we want to transform Schrodinger's equation to spherical coordinates instead. The thing is, when you do that, you have those second derivatives of x, y, and z, and going from dx, dy, dz to dr, d theta, d phi brings along some extra pieces like r and sine theta. One of the key points, though, is that to get to the solution, it turns out that when you go to r, theta, and phi coordinates, Schrodinger's equation becomes separable, meaning you can look at each of these pieces just apart from each other, and then you kind of just smash them back together to get the full solution. So there's this kind of capital R, capital theta, capital phi that are the functional form that you get for the solution that has the radial dependence, and then there's the solution that has the theta dependence, and the solution for the phi dependence. Should note that when you talk about spherical coordinates, it's unfortunate because what you call theta and what you call phi will be different depending on who's saying which is which. To be clear, we're saying theta is the angle from the z-axis. So that's that. Yeah, so we'll see some of the actual functional forms of these solutions, but the big picture here is when you solve Schrodinger's equation in this situation, you get solutions, and these solutions are now indexed by 3 numbers. Still n, the same n we had before, the principal quantum number, but we also get these other indexes, L, the angular momentum quantum number, and m, the angular momentum projection quantum number. And we'll be talking plenty about these, so we'll get more into them. And as it turns out, the different parts that make up the full solution, right, the radial, the azimuthal, and the polar parts, they each depend on these indices, on some of them, not all of them. So the radial one will depend on the principal quantum number and the angular momentum quantum number, the theta just on L and M, and phi just on M. And also out of this solution, you have restrictions on what these numbers could be, right? There's certainly certain allowed quantum numbers. So n is the principal one. It kind of sets the tone for everything else, and it can start out at 1, it can go 2, 3, 4, 5, 6, 7, it can go as high as you want, but it can't be 0, it has to start at 1, and then go anywhere up there. And so whatever n is tells you what L could be. So L can be 0, and it goes up from there, 0, 1, 2, 3, all the way up to n minus 1. So if n is 1, L can only be 0. That's it. If n is 2, L could be 0 or 1, etc., etc. And then finally m depends on what L is, which also depends on what n is. So m also depends on n, but we'll write it in terms of L here, and generally it's written in terms of L. But m, the angular momentum projection, can only run from minus L to plus L. So if L is 1, m can be minus 1, it could be 0, it could be 1, plus 1. So they're all integer values, and basically once you have the principal quantum number, n, the other ones will follow from that. Or the possible ones will follow from that. So a state could be like n equals 2, and L equals 1, m equals 0. That's a possible set. And here you go. Here are some functional forms of these different solutions. So again, remembering that there's these just allowed values that these indices can have. So for this very simplest one, if n is equal to 1, right, L has to be less than n, so L can only be 0, and m could only be minus L to L, well, it's just 0. Right? So when n is equal to 1, there's just one possible result for L and m, 1, 0, 0. This is what then the wave function looks like for 1, 0, 0. And it's fairly simple. It's decaying exponential. That's pretty much it. Oh, I should note too that there is going to be another index, which unfortunately also is m, that will come about pretty soon. And so we'll start labeling this m with a sub L, because it's related to the angular momentum quantum number. And then later we're going to get one that's related to something called spin, so we'll have a sub S. So then what about if n is equal to 2? Well, there's a number of possibilities, but one of them is just that L is 0, and then m has to be 0. And that's what the wave function looks like for that state, where now it's still this exponential, but there's also this polynomial that ends up coming into play, and so the overall picture looks a little bit different. These are the simplest wave functions you can get out of this solution to Schrodinger's equation, but they're still fairly complicated, and we're not going to worry too much about them. I don't know, maybe you'll have to do something with one of these in a homework problem, but other than that, they're complicated. We'll look at the plots or sort of graphs of them, graphs of their square magnitudes, because that's what gives us probability. So that might give a better idea of what these things actually look like, or what the results of Schrodinger's equation are telling us. But anyway, you keep going up. So n is equal to 2, you could also have had L equal 1, right? Because L has to be 1 less than M, at least 1 less than M. And in that case, with L is 1, M can be minus 1, 0, or plus 1. Right? These are the possibilities. And again, you still have that exponential. Each one of them also looks like it has this really simple sort of linear polynomial. And we start picking up these other parts, which are these trigonometric functions, right? Sine, cosine, these oscillating functions. And then some of them even also have this imaginary exponential that comes in. So the things get quite complicated quite quickly. So we'll get some more pictures later, but I just quickly wanted to get at that probability just a little bit. So recall that if we want to know what the probability of finding an electron at some position in space, now we're talking about a three-dimensional space, not just along a line that we did in the last chapter, because we now have a three-dimensional wave function. Well, we get a probability density by multiplying the wave function and its complex conjugate. So this is now where it starts to become more important, or it can become more important, that you do the complex conjugate and then also multiply the original wave function. Because some of these wave functions, some of these states, actually have complex parts, right? And you don't want those if you're talking about probability. You need real values in order to give you probability. Anyway, looking at just these first two states, where n is equal to 1, L is equal to 0, M is equal to 0, or the n is equal to 2, but L and M are still 0, if you do that complex conjugate multiplied by the original wave function, another way of saying that is the magnitude squared, and you plot that probability distribution, they look like this. So when n is equal to 1, L is equal to 0, we get this top picture, and sort of the brightness is telling you about the probability. So it's a like three-dimensional kind of cloud that's most dense in the middle and starts to get less and less dense, meaning that you're most likely to find the electron closest in the middle or closest in the center of that spherical volume, and then it gets less and less likely that you'll find it further and further out. For n equals 2, but still L and M equals 0, we sort of get this like nested sphere. You have this part very close to the center of the sphere that's pretty highly likely to be found. Then you kind of have this dead zone, and then you have this shell around that that's also has a fairly good probability overall, but then it still dies off as you get further away. All right, well, let's look at part of this example at least. We're just going to enumerate some of these states and see how many possible states there are when n is equal to 3. You know, recall that basically L has to be less than n, anywhere from 0 to n minus 1. If n is going to be equal to 3, well, L can be 0, L could be 1, L could be 2. Can't be 3, it's got to be 1 less than n. And then, how many possible values of m are there then for each one of these? Well, if L is 0, only possibility is m is equal to 0, little sub L. So we'll say that that's just the one possible state there. If m or L is equal to 1, n could be minus 1, could be 0, it could be plus 1. 3 possible states there. And then finally, if L is equal to 2, right, m could be minus 2, it could be minus 1, it could be 0, it could be plus 1, it could be plus 2. 1, 2, 3, 4, 5 states there. So the total possible amount of states, 1, 2, 3, 9. There you go. Not all that complicated, but there are these rules for which states are allowed, which values of L and M are allowed, depending on what the principal quantum number is, what n is. As it turns out, understanding the atomic structure, understanding atoms, how they act, ends up relying quite a lot on the concept of angular momentum. And you don't necessarily see that because we didn't go through the solution or go through the steps to find the solution to Schrodinger's equation there, but the indices L and also M are very much related to angular momentum. So let's just do a quick little look back at angular momentum, or recap. And in general, the angular momentum of an object is a cross product of the radial vector, which is the vector pointing from the rotation, wherever the axis of rotation is, to the point that's rotating, and that's crossed with the linear momentum of that object. And again, we're still kind of thinking along the lines of Bohr's model, where the electron is sort of in these circular orbits around the proton. So if you do have something that's moving in circular motion, the angular momentum sort of simplifies, right? Because the radial vector and the linear momentum are always perpendicular. And the magnitude, at least, of that object's angular momentum, we can just write as the radius that it's moving at from the axis of rotation, multiplied by the mass of that object, multiplied by its linear velocity, or its linear speed. I'm not even talking about vectors anymore. In this diagram, you see this like kind of blue dotted line is sort of meant to represent the circle that some object is rotating, see its speed, and the angular momentum vector points perpendicularly out of the area that's kind of being drawn out by that circle. So that's the angular momentum. It points in a particular direction, and it has some magnitude. The magnitude, at least, right, pretty simple. They're just R and V. Its exact direction can be, maybe difficult, but the projection of the angular momentum along the z-axis, if we're talking about spherical coordinates, is pretty easy. It's just that magnitude multiplied by cosine of theta, right? Theta was the angle measured from the z-axis. So we have angular momentum, and then we have its z component, or its projection along the z-axis. And in what follows, a lot of emphasis is put on the z direction, right? The projection of angular momentum, or projection of things along the z direction. That is really just a convention. The z direction is picked as sort of the special one. It's not actually special. When you define a coordinate system, you could point the z direction whichever way you want. And it's just sort of by convention, and possibly also because spherical coordinates are set up to work well this way, that the convention is just to kind of pick z as the special direction. And so you align things with that, you look at the projection of things along that direction. It could have been another direction. And you could just turn your whole coordinate system in a different direction already. And here you go. The angular momentum orbital quantum number, L, is actually associated with the angular momentum of the electron orbiting around the proton. The magnitude of that electron's angular momentum, its orbital angular momentum, has to do with the index L. So L plus 1 times L, square root of that, multiplied by h bar, Planck's constant over 2 pi. That tells you the magnitude of that electron's orbital angular momentum. And of course, this also means that an electron's orbital angular momentum is quantized, right? Because L, the little l, is an integer value, right? It could only be 0 to n minus 1. So that also means that the magnitude of the electron's angular momentum is quantized. You can only have certain values. And so if you think back or look back in your notes when we were talking about the Bohr model of the atom, it was the angular momentum of the electron we said was quantized there, but it was quantized in terms of n, the principal quantum number. So this is a difference now in the Schrodinger model where the magnitude of the angular momentum comes out to be related to this new index. It's not just n h bar, it's that square root L plus 1. It turns out, though, that there is something very much like Bohr's idea of quantized angular momentum, and that is the projection of the electron's orbital angular momentum along the z-axis, or along n axis, but again, choose z as the special one because we want to. So if you do look at the projection of the angular momentum along the z-axis, it's quantized and it's just in terms of m, the angular momentum projection quantum number, times h bar. And again, that's that m, it's not mass, it's an index, and we'll also see it as n sub l, because we're going to get another m in a little bit. Just looking at this picture, you can see that the projection of angular momentum along the z-axis is just the total angular momentum, the magnitude of that total angular momentum, multiplied by cosine of theta, the angle from the z-axis. And remember, m can take on any integer from minus l to plus l. It's interesting to note then that What we get from Schrodinger's equation is that we can know the magnitude of the electron's orbital angular momentum, but we don't actually get all the components of that. We don't actually know the vector form of its angular momentum, and in fact we can't. We only know the magnitude, and we can know its angular momentum along one direction, or one component of its angular momentum, which we generally choose the z component. Just an interesting thing to know. So you maybe enjoy terminology or that kind of thing. It's not necessarily my thing, but we have some terminology that we gotta get to, and that has to do with talking about these different states, talking about the orbital angular momentum of different states that are solutions to Schrodinger's equation or the hydrogen. So there's just sort of this historical precedent that ended up naming the different L values, or at least the first few L values, and that had to do with the fact that when you start to see stuff about these states, the energy of these states, that was in atomic spectra. So the values of L started to get some names, and we still use not necessarily the names, but the letters to specify some of these states. So for instance, when L is equal to 0, that means there's no overall magnitude of orbital angular momentum. That was what was called the sharp line, the sharp state, right? So it's given the letter S. When L is equal to 1, well, now you have some amount of overall angular momentum, which in fact when L is equal to 1, you end up getting the square root of 2 times h bar. That was what's known as the principal spectral line, and so it gets the letter P, so forth and so forth. You get diffuse, D, fundamental, F, and after F, they just start going in alphabetical order. So S, P, D, F, G, H, I, J, K, so that's where those letters come from, and that ends up being used in what's called spectroscopic notation, where you can write the state of an electron in an atom, or you can put multiple of these notation things together and write sort of the state of the atom overall, multiple electrons. So for instance, if you want to write the state n equals 1, L equals 0, you write 1s. N equals 3, L equals 1, 3, P. P is for 1. Orbital angular momentum quantum number 1, write P. So, yeah, now you know. And getting back to what it means that the magnitude of the electron's angular momentum, the angular momentum associated with it orbiting around the proton, what it means that that is quantized, well, we can visualize that by just kind of drawing out some states of angular momentum. If we use that relation for the magnitude of the angular momentum and then its projection along the z direction, right, there was that cosine of theta that related them. So since L and M are both integers, what that ends up meaning is that the angle that the electron's angular momentum vector ends up making from the z direction is also quantized. You can only have certain angles, and that depends on M and L. We have just some examples here, say, of L equals 3 on the left. All the possible values for M would be minus 3, minus 2, minus 1, 0, 1, 2, 3. If you put those values into this equation, you see that there are these angles that the overall orbital angular momentum can have from the z-axis. 1, 2, 3, 4, 6, 7 possible angles. But again, since we only know the projection of this angular momentum in one direction, right, just the one component, the z component, we can't say that this L is just pointing in one particular like xy direction. It basically has to be this kind of on a cone, right? If you look at the picture on the left with L equals 3, imagine just kind of rotating that around the z-axis, and that's sort of your possible angular momentum. And in this picture here, looking at L equals 2 would be 5 possible m values, so 5 possible angles, but we don't actually know anything in the y and z direction, so that angular momentum is just along this cone somewhere, right? These different cones. So let's just look at an example where L is going to be 1. What are the possible angles that the angular momentum of this electron could make from the z-axis? So from our last slide there, just jump right to this equation for the angle from the z-axis, theta, looks like that. So if L is equal to 1, there's 3 possible values that m could take. It goes from minus L to plus L, so it could be minus 1. That looks like, put those values in, you end up getting minus 1 over root 2, which is 135 degrees. So m equals minus 1, right? That's the 135 degrees is so below the xy plane. That's the cone that this angular momentum vector could be on, or is on. What about L still equal to 1? What about m equal to 0? Pretty straightforward. That's inverse cosine of 0, which is 90 degrees. We're also restricted. The angle from the z-axis can only be between 0 and 180. So inverse cosine of 0, 90 degrees, that's actually in the xy plane. So this angular momentum vector can be in the xy plane, or is in the xy plane when m is equal to 0 there. Finally, what about when m is equal to plus 1? Well, we get almost the same thing here, but this is plus 1 over root 2. Root 2. Which ends up being 45 degrees. So 45 degrees from the z-axis, that's the cone that this m equals plus 1 angular momentum is going to be at. And that's it. Those are the only possible angles. Those are the only possible angular momentum states that you could have when L is equal to 1. It's quantized. Okay, so let's go back to a bit of probability. Remember, the reason that the wave function is useful at all is because when you take its square magnitude, also same thing as doing a complex conjugate times itself, when you do that, you get a probability density, and if you integrate that probability density, you will get the probability of finding the electron, say, in whatever that region was, that volume was that you integrated over. And it is now a volume, right? In the last chapter, we were talking about the wave function, but it was one-dimensional, so it was just along the x-axis. Now we're thinking about 3 dimensions. The integral here is a 3-dimensional integral, and yeah, so it needs to be over volume. We're not going to get too much into using the functions themselves here. That, say, besides n equals 1 and 2, it gets quite complicated, difficult to work with. But just wanted to point this out to kind of remind you about the wave function giving us probability and how it does, and then we can start to understand a little bit about some of the shapes of atoms that we get for these different states. And if you do think about sort of the simplest state, or states where L and M are both 0, there's no overall angular momentum, then those wave functions end up having no theta or phi dependence, and this integral becomes a bit simpler for the probability where, you know, the dV becomes, I think, r squared sine theta dr d phi d theta, right, for a spherical infinitesimal volume element. That's what dV becomes. But if there's no theta or phi dependence, then the theta and the phi components end up giving you 4 pi. So this is what that looks like if you were to graph the square of the wave function, or the magnitude square of the wave function, as a function of r. You just get this bump, this sort of peak dies off. And this is a graph, you know, 2-dimensional graph as a function of radius. So if you want to imagine what the probability looks like, then we kind of have to think about, well, kind of rotating this picture in 2 different dimensions, but you end up getting this sort of spherical shell. When L is not equal to 0, the wave function is no longer spherically symmetric, so you start to have these shapes that can have particular directions to them. So when L is equal to 1, say the probability density, or the wave function squared, ends up looking like the sort of dumbbells, and so they have this sort of directionality which is along the axis of the dumbbell, and that can be pointed in these different directions. And sometimes you'll see pictures like this of what are now called orbitals, or not orbits for electrons, are called these probability clouds, you know, orbitals. You see pictures like this that are very hard edge boundary sort of thing. Usually what they're graphing or showing you is the region of 90% probability. So it's the distance that you go out, where if you integrate out to that region, that's including 90% of the probability you'll find the electron there. So there's still probability you could find the electron away from these areas, but 90% of the time you'll find them in these, within these shapes. And like I said, the functional forms themselves can be quite complicated, but we can get an idea of what these probability clouds look like, these orbitals, just by plotting some of them. So I showed you n equals 1 and 2 and L equals 0 states earlier. There's that first two up there. But now showing you a few more. We're saying now n equals 2 and L equals 1. It's the same picture actually as the last slide. It's just instead of showing these hard edges, we're graphing it as like the color, the intensity of the color is the probability, and so it just kind of fades off as you get further away. Very quickly, you can get these pretty complicated shapes, like n equals 3, well, at least the zero angular momentum state, when L is 0, so remember the square root of L plus 1 times h bar, that was the angular momentum of the electron. So when L is 0, these are zero angular momentum states. So those are all fairly straightforward, you just end up getting sort of more and more spherical shells. However, when n is 3, when L is equal to 1, almost looks like a Pokeball kind of thing. And remember that this is like a slice through the middle of this picture, so this is a three-dimensional thing. Or when L is equal to 2 here, we end up getting this sort of four-leaf clover shape even. So if you've done much chemistry, then you've probably learned about orbitals, the shapes of different atoms, and those shapes end up influencing very strongly the way that those chemicals or those elements interact with each other. And so that's where these shapes come from. Solution to Schrödinger's equation for these different principal quantum number states and different angular momentum states. And remember that m is the projection along the z-axis. So these are just, for m, you're just sort of orienting these shapes in different directions. Because trying to understand the atomic spectra, they kind of kicked a lot of people into having to deal with quantum mechanics, having to come with this idea. And then further studying atomic spectra gave us sort of more reasons to add to it and to understand some more of the complexity. So in a way, looking at the atomic spectra, like the finer our resolution was able to get, the more lines we were able to see. And so those lines, well, we needed to say why there were these other lines now. And in order to understand some of the very fine lines, we need to start thinking about the magnetic dipole, or the magnetic moment of this orbiting electron. And so think back a little bit to magnetism. We learned about magnetism. If you have a current that's flowing in some sort of a loop, then the magnetic moment or the magnetic dipole of that loop has to do with the current that's flowing and the area that loop is encompassing. So if it's just a current carrying loop or wire, then that's what the picture looks like, and that current is positive. So we have a right-hand rule that tells us that the magnetic dipole moment is going to be pointing upwards, like that. And that was important or useful because magnetic fields can exert torques on magnetic dipoles, on magnetic moments, and the energy, the potential energy of, say, this loop could be understood by looking at the combination or the dot product of that external magnetic field and its dipole. So in the case of an electron, right, still kind of thinking like Bohr's model, where we have this electron just zooming around a circle. That electron is charged, it's moving, so that amounts to a current, where the charge and the making of this current is now negative, so the magnetic dipole is actually pointing in the opposite direction because of that negative charge. We can define this magnetic moment. All we have to do is go back to our analysis of Bohr's model to say what's its velocity. So if we know what its velocity is, we can work out that amount of current, right? It's change in current or change in time. And the area we can also get from Bohr's model because it has to do with the radius of that circle. So you can work out that magnetic dipole for the electron, and you can end up actually relating it to the angular momentum of the electron. And the book actually, I think, goes through it pretty well, so I'm not going to step through that. But you end up getting this relation, where the magnetic dipole is equal to minus some value, some constant values, multiplied by the angular momentum. Yeah, so like I said, that's important because that magnetic moment now, due to the electron orbiting the proton, can be affected or can have different amounts of energy overall if it's in some kind of external magnetic field. So the fact that it has this dipole moment, this magnetic dipole, if you have this external field, that external field is going to want to exert a torque on that magnetic dipole, meaning that when it's aligned, it's going to be a lower energy state. When it's anti-aligned, it's going to be a higher energy state in between there and other states. But the energy due to this dipole interacting with this external magnetic field affects the overall energy of the atom. And again, you can look at the particular breakdown in the book, I believe, but we end up getting that it's m, right? Remember, m is the third quantum number, it's not mass, multiplied by that mu b, where that's a collection of other constants, the electric charge and the actual mass of the electron, and it's known as the Bohr magneton. It's a constant value. But those things multiplied by the strength of the external magnetic field. Looking at that, remember m is an integer value, so this energy is quantized. It can only take on certain numbers. For instance, when L is equal to 1, remember m can be -1, 0, +1. That means that for this electron, or for this atom, in this external magnetic field, there are now 3 sort of extra possible energy states due to the fact that this magnetic field is interacting with the magnetic dipole moment of the electron. And if you look at the atomic spectra of, say, like a hydrogen atom or some atom that's in an external magnetic field, you actually can confirm that this model is correct because that external field is actually splitting these angular momentum states into multiple substates, so sub-energy states. But when L is equal to 1, remember m can be 3 different values, -1, 0, or +1, meaning that that external magnetic field is splitting the energy of that state into 3 different substates, right? Closely spaced, because that energy difference is pretty small, but they're there. And the larger that external magnetic field is, the larger the splitting is, right? Meaning that our understanding, our model for this magnetic dipole moment of the electron is a good one, right? That's what Zeeman is telling us here, or the Zeeman effect, is that splitting due to the external magnetic field. And so when L is equal to 2, right, m can be -2, -1, 0, 1, 2, right? 5 states. So you have the L equal to 2 spectral line in an external magnetic field ends up getting split into these 5 separate lines. That's so great. It gives us some confirmation that our thinking about the electron and the atom overall is going well so far. But it also has useful applications where you can get a measure of the magnetic field in some distant region by looking at the particular spectral lines that you know, say, is due to this L equal 1 transition to L equal 0, and you look at how split those sub-energies are, right? For L equals 1, you have these 3 sub-energies for m -1, 0, and +1, and they're only there if there's an external magnetic field that that atom is in, and the stronger that field is, the further apart those lines get split. So if you look at that particular emission line, say from light coming from the sun, then you see how split those lines are. That will tell you how strong the magnetic field is in the region where that light came from. You can do this analysis and make these magnetograms, cool name, of the magnetic field on the sun, right? And these bright and dark areas are showing very strong magnetic fields, or lots of magnetic activity.